I want to talk about more exciting things you can do with this EPR state. And part of that is a warm-up for next time, where we're going to see this CHSH experiment, which was the exact subject of last year's physics Nobel Prizes. They were won for actually thinking of and demonstrating another party trick that's 4 lines long that you can do with the EPR pair, which I will show you next time. But we're going to warm up with it by learning more about the EPR pair state today. Okay, so as a tiny teaser, let's say you start from the mystical state EPR 0, 0 plus 1, 1. And I'll just show you a very minor thing. Say Alice does so actually imagine that Alice and Bob get together and make this EPR pair with that 4 lines of code, and then they do this thing that we only say to illustrate the vividness of it. Alice takes A and walks far away, and Bob takes B and walks far away. Say Alice does toggle A on her qubit. Then what's the new state? Well, this one's easy. It's just a 1, 0 plus 0, 1. Okay, which normally we sort these, so I'll say 0, 1 plus 1, 0. Okay, now forget that for a moment and say, on the other hand, instead, say, starting from EPR, Bob does toggle on his qubit. What's the new state? Well, this is also easy. Just toggle the second qubit, so it's 0, 1 plus 1, 0. Hey, presto, these are the same. So you might not think that's particularly amazing, and it's not. But later we're going to see some similar things where you'll be like, whoa, this is really amazing. So I show you this to say it's not maybe that amazing. But a funny way you could say this is, suppose Alice and Bob make the EPR pair and then they split up and go far apart. You could say Alice can remotely do toggle B by locally doing toggle A. She can it's as though she could do toggle B on Bob's qubit by toggling A on her qubit. Because, look at it, if she does toggle A, it gets the joint state to this, which is the same thing as if Bob had done toggle B, and vice versa. So it's a property of this joint state that somehow Alice can locally do things on A that are equivalent to Bob locally doing some other things on B. And that's kind of interesting. So in fact, here is a cool fact, which we're going to prove today. And then we're going to use, well, maybe even a generalization of this cool fact next time. But it's a generalization of this, so I'll call it a cool fact. Okay, so starting from EPR, if Alice does U on A, where U could be any unitary, rotate 30 degrees, it's equivalent to Bob doing U transpose on B. And I'll remind you, what is U transpose? Well, it's the transpose matrix of U. If you think of U as a 2x2 matrix, you switch rows and columns. Or if you prefer path diagrams, which I know everybody doesn't, but it's the reverse path diagrams, where you just show all the arrows upwards rather than downwards. Or it's the same as U dagger in this course. Because in this course, like, everything is real. So this is like where you do transpose and also complex conjugate, but we don't use complex numbers, so it's the same. And this is like the same as like the undo or inverse of U. And that's because U is unitary. So it's basically, I mean, long story short, this is like the undo of U. So like if this is rotate by 30 degrees, this is rotate by minus 30 degrees. Or if this is toggle, this is also toggle, because toggle is the undo of toggle. Okay, and that's like the more cool generalization of this fact. Okay, so we're going to demonstrate why this is true. And you could demonstrate it just by like writing out like a generic 2x2 matrix and like writing out the amplitude trees and like just doing the amplitude tree for U on A and getting like a bunch of numbers or letters and doing the one for U inverse on B and finally doing a long computation and be like, yep, they're the same. That's what we did here, but like the computation was super simple. But I'm going to try to do it in a more conceptual way. But really, you can bear in mind that like all the stuff I'm going to be talking about in the rest of the lecture is just like a nice organizational way of organizing math calculations. So the ultimate reason, the ultimate conceptual reason why this cool fact is true is, put it like Y in quotation marks, is because if you draw the EPR state in, you know, our favorite square way, I've drawn these pictures many times, this is 1, this is amplitude 0, 0, 1, this is EPR. If you draw it like this, and then kind of squint and say like, hey, whenever I see like 4 numbers arranged like this, I sometimes think of a 2x2 matrix. This like looks like this 2x2 matrix, 1, 0, 0, 1, which is like the most famous of all 2x2 matrices, right? This is the identity matrix. This is the matrix that corresponds to the operation on 2-dimensional space of doing nothing. Now this is still like, this is actually a 4-dimensional vector, right? This literally means this vector, 1, 0, 0, 1. So it's not the same as a 2x2 matrix, but nevertheless, sometimes it's good for organizing your math calculations to think about it this way. Okay, so let me introduce some notation. This is like, this notation has nothing to do with quantum per se. It's like, I suppose, linear algebra notation. If you have a 2x2 matrix M, W, X, Y, Z, maybe it should be a non-zero matrix. Well, okay, it's any matrix. We write vec M for this vector, W, X, Y, Z, or equivalently, the 2-qubit state, W00 plus X01 plus Y10 plus Z11. Okay, this is an unnormalized state, but that's fine. I guess it's, if all 4 of these are 0, then like all zeros is an illegal state, but never mind. Okay, so this is just some notation for writing an unnormalized state in like, well, taking a matrix and viewing it as an unnormalized state. And of course, vec stands for vector. And the key example of this notation is vec of the 2x2 identity matrix is exactly EPR. Okay, so what is the advantage of thinking about these 4 numbers as being arranged into a 2x2 matrix? Because a matrix is really supposed to mean an action, right? A matrix represents a linear transformation, which is like an action or a change on space. That's not what a vector means. A vector means like a point in space. So like, why would you try to take this nice vector and think of it as a matrix? Well, it just helps you organize computations. So to explain what I mean by that, I'm going to write down what I'll call fact 1. And it's this. Suppose you have 2 qubits, A and B, are in the state, vec M. Okay, so they're in some state, W, X, Y, Z, but it's the vec of the M matrix. And now say Alice does the unitary operation U on A. Okay, that's like always like U is a 1 qubit unitary. It's always the case where it's like a little bit annoying. You have to remember like how to like organize the amplitudes. And this fact just tells you like a simple thing. Then the new state is vec of UM, where this is like 2 by 2 matrix multiplication. So that's kind of convenient because you can a little bit go on autopilot and you're like, okay, M is a matrix, U is another 2 by 2 matrix. I know how to multiply 2 by 2 matrices, so I'll just do that. And then if I write those 4 numbers out, that's the new state. So that's kind of convenient. So let's check this. So the state starts out like this. Let me draw it over here. W, X, Y, Z. This is just like the generic starting state. But drawn in this like nice square way. A is going up and down as it usually does, and B left and right. Okay, so now what happens? Alice is doing U on A. So how do you do that? Do U on A? You pair up the basic states according to the unchanging part, which is B in this case. So you're like, okay, here's the B equals 0 side, WY, and here's the B equals 1 side, XZ. And now, like it type checks, like this is a 1 qubit state, WY, this is a 1 qubit state, XZ, unnormalized. So you just can apply U to that. So, I mean, when we do this, it's like the left edge changes to, well, U, WY. Okay, this is a 2 by 2 matrix. You can apply to it to a height 2 vector, and whatever the result is, that's what goes in here. And the right edge changes to U times XZ. But like, basically that's how matrix multiplication works, right? Like, if you go back to, I don't know, 11th grade or whenever you learned how to multiply 2 by 2 matrices, if you do like a 2 by 2 matrix times U times W, X, Y, Z, well, this is what happens. The new first column is U times WY, and the new second column is U times XZ. So that's it. That's the end of the proof. Okay, that's cute. So, well, now we need fact 2, which is about the same thing but doing B. And that one's like a little bit more annoying, but it's like kind of fun. So let's do that. So fact 2. Same story, but Bob does V on B, where V is some other 1 qubit unitary. So a 2 by 2 matrix. Then the new state is vec of M times V transpose. So notice the transpose. Like, notice that like here, U is acting on the left qubit, so we kind of left multiply by U. Here, B is the right qubit, so we kind of multiply on the right. Also have to put a transpose. So why is this true? Again, I mean, it's just, you just write down the definitions and it checks out. But the way to see it is, okay, if you start from this state, which is where we're, again, starting, like what happens from a quantum point of view when you do V on qubit B? Well, again, it's like you pair up the qubit basic states according to the unchanging part A. So like here's where A is 0, and we kind of do V on this qubit. And here's where A is 1, and we do V on this qubit. So basically, it's going to be like the same picture, except the notion of rows and columns gets swapped. So, well, the outcome is that the top horizontal edge becomes like V applied to Wx, and the bottom horizontal edge becomes V applied to Yz. So it's basically like kind of like, oh, we sort of wish that like we took this horizontal edge Wx and like it were vertical here, and we took this Yz and it were vertical here. If that were the case, then it would be just like before, and we'd multiply on the left by V. But that's the same as transposing this picture, right? It's also the same as doing a swap operation on A and B. But okay, like just in order to describe with like matrix notation, how do you like start from a matrix that looks like this, a 2x2 matrix that looks like this, and accomplish this? Well, it's basically this. Let me not erase that. Okay, I'll put it here. This is terrible board usage, but maybe the way to do it is like the new state is, first we take like Wx, y, z, which is the vec of M, and we like transpose it. And then it'll look like Wx, y, z. And then we multiply on the left by V, because we want to change Wx to V applied to Wx, and we want to change Yz to V applied to Yz. And then we have the right things, but they're on the vertical edges rather than the horizontal edges. So we have to kind of like transpose these things back. Well, I should say the new state looks like the matrix this. And then if you remember a little bit about matrices, the transpose of a product is the reverse product of the transpose. So this is M transpose transpose times V transpose, which is like M times V transpose. Okay, and that's this. Okay, any questions about that? Great, so fact 1 and fact 2 are just very convenient little calculational tools. But maybe now you can start to see why it's sort of particularly exciting when the state is EPR, because it means this matrix M in the middle is the identity matrix. And like, it's always cool to have the identity matrix, because the identity matrix has the property that you times it by anything and you get back that anything. Okay. So let's just think about that briefly, and we'll see the proof of the cool fact. Okay, so recall, I think I just erased it, but EPR state, which is 0, 0, plus 1, 1, is like the vec of I, the 2x2 identity matrix. So fact 1 tells us that if Alice and Bob have 2 qubits and they start in this EPR state, And then Alice does any unitary operation U on her qubit A. The new state is, when you draw it as a 2 by 2 square, what matrix does it look like? It looks like U times I. Oh, but this is nice. As I said, this is just U. So this is vec of U. And bear in mind, this is like an unnormalized state, but that's okay. So for example, suppose, I'll do an example over here. Say U was like, remember like 15 lectures ago, we introduced this one qubit operation called clockwise, which really, I didn't say it at the time, but it was like rotate by about 37 degrees, but its representation was this, 0.8, negative 0.6, 0.6, 0.8. Okay, this is our favorite like little 2-qubit operation because these numbers were like nice 1-digit numbers. But it's really like, oh sorry, this should be like negative 37. Because clockwise for mathematicians is negative. Yeah, so if you start in the EPR state and Alice does this clockwise operation, a rotation by minus 37 degrees, the new state is like vec of this, which is, well, 0.800 plus 0.601 minus 0.610. Let me write it like this, minus 0.610 plus 0.811. Okay, it's just the same 4 numbers, but like arranged like this. Okay, and this is an unnormalized state. The sum of the squares of the amplitude here is 2, but that's okay. Okay, but like, we'll just say on the other hand, because I'm illustrating the cool fact here, on the other hand, fact 2 says that if starting from EPR, instead Bob did the undo of U, U transpose or dagger on B, then the new state is vec of, we write multiply by the transpose of this. So I times U transpose transpose. Okay, but U transpose twice is just U, and then I times U is U. So this is again vec U. Okay, and these are the same. So that like justifies this cool fact. And it justifies, here, in this case, U transpose is what we used to call counterclockwise, but it's like rotation by positive about 37 degrees. It's this matrix, 0.8 minus 0.6 minus 0.6, oops, plus 0.6, 0.6, 0.8. And this fact 2 says that like, if from the beginning Bob did counterclockwise on his qubit, you would also get to this state. And that's pretty neat. So again, has this like kind of weird effect where you could say like, oh, Alice can accomplish like rotating B by 37 degrees, positive 37 degrees, remotely by like locally doing rotation by negative 37 degrees on her qubit. Or in other words, yeah, another thing you could say is, to continue this example, if Alice does clockwise on A, that's the same as doing counterclockwise on B, which Bob could undo by doing clockwise on B. Just restating this, but like then Bob does clockwise on B. These like cancel. You get back to EPR. So that's like starting from EPR. Okay, so when you just like do the math, it doesn't look very interesting. But then if you think about it in this way, where like Alice can remotely do something to Bob's qubit by doing something locally to her qubit, it becomes more interesting. And we'll see a very interesting illustration of making this work for you next lecture.